The phenomena that happen when colloidal nanoparticles are mixed with liquid crystals have been of main interest in the soft matter field. In this talk, we will focus on the heterogeneous with transition pattern which occurs in the nanoparticle-doped nematic liquid crystal. What will happen when spherical particles are dispersed in an anisotropic fluid, such as nematic acid? In the idealized scheme of nematic phase, the rod-like acid molecules would align roughly along the same direction. If the acid molecules are anchored on the dispersed particle, the director field will be deformed, and the consequent orientational conformation of the acid molecules would result in a topological defect formation around the particle. Plum and Waite have shown that this defect formation would assemble the suspended particles to minimize the deformation energy of the medium. Different from the perfect nematic alignment, when the nematic acid material, like 5CV, is confined between two glass substrates, the heterogeneous planar orientation of the nematics results in the Schlieren texture under the cross-polarizers. When the spherically shaped nanoparticles are doped, the particles tend to be expelled to the defect sites, accumulate, and agglomerate, as can be seen in these images under the crossed and parallel polarizers. On the other hand, the metallic nanoparticle doping can affect the phase transition pattern of 5CV in IN as well as NI transitions. When pure 5CV in the isotropic phase is cooled, the phase transition pattern is so simple. The nematic region appears with a smooth front, and this front just sweeps the field of view, and it is the same for the NI transition. However, when the 5CV is doped with gold nanoparticles, we have the development of small nematic domains in an isotropic background, and these domains grow to fill the whole specimen. In the NI transition, where the 5CV molecules are anchored on the surface of gold nanoparticles, the same pattern of domain growth has been observed, but this time the domains represent the melting behavior. So, based on these previous works, we can ask the following questions. First, how NPs are dispersed in the liquid crystal matrix? If the nanoparticles are agglomerated in the defect site, what are the morphology and size of the NP agglomerates in the SC? And finally, what causes the inhomogeneous pattern of NI transition? Here our objectives are, by using 5CV and iron oxide nanoparticles, to achieve direct in situ visualization using cryo-TEM, focused on the NI transition process, particularly the spatial patterns, and to find the role of NP agglomerates in the NI transition. When we mix the nanoparticles at a low amount and prepare a surface-coated glass cell with homeotropic alignment, the local deformation in the 5-sphere orientational order at the agglomerates can be observed. If we check this in a heterogeneous planar alignment, we have more accumulation of particle agglomerates at the defect sites as increasing the doping amount. And interestingly, granules are detected at the nematic phase region, which correspond to the agglomerates of the nanoparticles. Now let's have a close look at these agglomerates using cryo-TEM, which allows to observe the structure of the agglomerate in situ. The 5 CB nanoparticle mixture, as shown under the crossed polarizers like this, is deposited on a perforated carbon-coated grid, rapidly bloated and plunged in a liquid ethane to finally form a very thin vitrified film of the mixture. Under the cryo-TEM at a low dose of electron beam, we find more or less elongated morphology of the agglomerate, and in higher magnification, it is confirmed that the particles are closely packed in sphere-like aggregates to form larger clusters. From these images, we can directly measure the particle size, the center-to-center distance of the adjacent particles, and the size of the sphere-like aggregates. From the image-based analysis, we see that the mean nanoparticle size is at 5.8 nanometers, and the surface-to-surface spacing between the particles in the sphere-like aggregate is 1.9 nanometers, which corresponds to the Oleg axis train length. This means the closely packed particles were 30 to 40 nanoparticles in a sphere-like aggregate, and we assume that the formation of the sphere-like aggregates formed first and then migrate and cluster at the defect sites. So far, we have focused on the morphology, structure, and size of the nanoparticle aggregates in the nematic medium. Now let us see what happens in the Ni transition of the particle-doped 5 CB. At a low doping ratio, the thin glass cell confined mixture shows a fast melting at a very low heating rate with the smooth front of the nematic to isotropic transition. If we have a close look at the nematic regions during melting, we see the shrinking of nematic domains during the Ni transition as a time series, with the granules in the nematic domains appear more and clearer with time, indicated as arrows in the images. As was confirmed in the cryo-TEM, the particle agglomerate size is a few hundred nanometers, which act as the scattering center in the visible spectra, and these granules become crowded as the nematic domain contracts. The magnified view of the granules provides the size distribution, where the mean size of the granules is around 2 micrometers, with more granules as increasing the doping amount, and most of them are suspended in the nematic region, and finally clustered in the defect sites, as shown in the next slide. This is the case of higher doping ratio, where more granules are found in the nematic matrix. With the same cell thickness and heating ratio, we observe more inhomogeneous front between nematic and isotropic regions, and see that the growth of isotropic domains from the granules, which can be exemplified as shown as this page. And in this series of snapshots, we see that the granules in the initial nematic matrix act as the nuclei for the development of isotropic domains. And after, the grown domains coalesce to be a larger isotropic domain. In conclusion, this work reveals, using cryo-TEM, how metallic nanoparticles are dispersed in an LC matrix, so that the morphology, structure, and size of the metal oxide nanoparticle aggregates are visualized in situ. And finally, we see that the MP aggregates affect the patterns of Ni phase transition. For the future study, the effects of the magnet field on the agglomerate structure and the phase transition behavior can be investigated. Finally, we thank Dr. Amélie Le Forestier at LPS Auxerre and Dr. Min Gao at LCI Kent for their help. We thank our team members, and finally, thank you for your attention.